Hello guys, welcome to my channel. This is Ehsan, and in today's video we're going to take a look at another electronic quiz. Here it's our circuit. This is our amplifier, and we're going to calculate the input resistance of this amplifier from the notes that we can observe from it. Here are some assumptions, and if you're new here, please give me a thumbs up, hit that subscribe button and also the notification bell, so whenever I upload a new video you'll be aware of it. Let's jump into it. This is the circuit, this is the assumptions, and these are all the possible options for this input resistance of this amplifier. Before we're gonna start using some calculations, KCL or KVLs, it is better to simplify this circuit. We're going to calculate the input resistance from this node. So anything before that is going to eliminate it. We're not going to look at them. Okay, I'm going to redraw the simplified circuit in here to better get the vision what we're going to do. This is our BJT NPN transistor. Here, this is our 4 kilo ohm resistor, and here this is our 12 kilo ohm resistor, and here VDD is going to be short circuited because in AC calculations relating to the resistance or the independent sources are going to be if there is a voltage source, it's going to be short circuit to the ground, and if there is a current source, is going to be open circuit. Now here we're going to look at input resistance from this node, and in order to do that we're going to put our test voltage in here. Let's call this Vx, and the current through it is Ix. Now by the definition, Ri equals to Vx divided by Ix. So we had to find the relationship between Vx and Ix in this equivalent circuit. Now I'm going to use a small signal parameters. I'm going to show a small signal parameters just into this circuit. If you remember, for this small signal, for this bipolar transistor, we have this small signal behavior. Okay, this is our small signal. This is R pi. This is V pi, and here this is GMV pi. If we neglect the channel length modulation, which is nothing about early voltage or RAO for this transistor. This is our base, this is emitter, and this is collector. Okay, now I'm going to use this small signal model and show it through this this circuit actually. So here this is our V pi. I'm not going to use V pi because V pi is exactly equal to Vx, so this node here equals to Vx. And how about this current? This current is GMV pi, and V pi is Vx, so this one is GMVx, and GM is already given 10. So this is 10 Vx. Okay, now I'm going to use, for example, node Y. Let's call this Y in here, and KCL, use the KCL relationships at node Y, and the voltage in here is Vy. So we had to find the relationship between Vy and the other parameters, Vx or Ix. KCL at Vy. So here Vy divided by 12, this current, plus Vy minus Vx divided by 4, this current, and this current here, 10 Vx plus 10 Vx equals to 0. Now for the sake of simplicity, I'm gonna multiply all of this into 12 to get rid of this denominator. Here it is Vy plus 12 divided by 4 is 3, so 3 Vy minus 3 Vx plus 120 Vx equals to 0. Now here we have 4 Vy equals to 120 minus 3. So here this is 115 with the sign minus Vx. So here it is Vy equals to minus 117 divided by 4 Vx. Okay, this is our calculation. Okay, this is one equation, and the other is going to use KCL at this node Vx. Now we can use this Vy into the next equation. Okay, here KCL at Vx, KCL at Vx, Ix it goes through it, so minus Ix plus Vx divided by minus Vy divided by 4, this current. And how about this node, this branch? This includes R pi. You had to see this R pi in here as you look at this a small signal model. So this is Vx divided by R pi plus Vx divided by R pi, and instead of R pi I'm going to use this one, 8 equals to 0. Okay, now here it is. Again, for the sake of simplicity, I can multiply all of this into 8 to get rid of this denominator, multiplied by 8. So here we have minus 8Ix plus 8 divided by 4, which is 2 Vx minus 2 Vy plus Vx equals to 0. So here what do we have? 2 plus 1 is 3, so 3 Vx minus 2 Vy, and instead of Vy I'm going to use this one. I'm going to substitute this expression instead of Vy. So minus 115 divided by 4 times Vx, all of it times Vx, and here we have minus 8 Ix. I'm gonna place it on the right hand side, so here it is 8 Ix. Now we can calculate Vx divided by Ix. These are just some constant. Okay, now we're gonna need some sort of approximation, okay, in order to calculate Vx divided by Ix. So here it is, on the numerator we have 8, and on the denominator we have 3 plus minus times minus is plus, and 2 with and 4 are just simplified 2 in the denominator. Let's get this 120 divided by 2, which is 60. Okay, which is 60. And again here we can have 8 divided by just 60. Okay, now what do we have for the rest? This one you can or 60 instead of 63, you can simplify this as 8 divided by 64. It's almost 8 divided by 64. So Ri equals to 1 divided by 8 kilo ohm approximately. This is an approximation, and if you multiply this by 1000 to make it equals to one of these options, which is in ohm, so 1000 divided by 8 equals to 125 ohm. So option C is the right answer. We need some sort of approximation at the end to clarify our result pretty well. Okay, now 125, this is our answer. I hope you like this video and this technique, you had to bear that in your mind, this small signal model, and use some sort of calculations in terms of KCL or maybe KVL to calculate the input resistance. And don't forget where to look. In each node that you're going to look at the circuit, you just put some test voltage and current to calculate the input resistance. Okay, I hope you like this video. If that's the case, please give me a thumbs up and share this video with your friend. I will see you on the next video. Thanks for watching.